Naikkan suara korang sikit. Okay. Okay, so yesterday Umar asked, why is the rate negative? And then the answer, you have your equation, which is a negative over here. Sekejap. I'm hoping this works. Okay. So yesterday we talked about this question and we discussed that the rate of change of the magnetic field is 0.09 Tesla per second. And in this question, it did not indicate whether the rate was decreasing or whether the magnet is pulled away from the loop. It doesn't mention anything of that. So I discussed this with my colleagues and we agreed that the rate should be positive and this question should be amended to find the magnitude of induced EMF. So the question only wants you to find the magnitude, no polarity. Find the magnitude of the induced EMF. Okay, so if this question only wants you to find the magnitude, then this equation, you can omit the negative sign. So N, this one over dt. So it only relies on the Faraday's law. Okay, remember Faraday gives you the magnitude of EMF, and when you have the negative sign, it gives you the direction or the polarity of the EMF induced. So most of the time, calculations, they only want you to find the magnitude. However, if they draw a circuit and they ask you to label the positive, negative, then the Lenz's law comes into play lah. Then you have to use the Lenz law. But selalunya soalan macam ni, dia akan suruh cari magnitude. Okay, so that is me answering Umar's question. Soalan Divya saya tak sempat tengok lagi. I will try to answer it today. Okay, so next example, a coil with 200 turns of wire, so N equals to 200, is wrapped on a square frame, 80 centimeter on a side. So this guy is a square, which means that we know that both sides should be the same. So area of a square is 0.18 times 0.18. They should give you something in meter squared. Okay, because it's a square. A uniform magnetic field is applied perpendicular to the plane of the coil. So you have a plane, so it's a square, right? It's a square. So this does not look like a square, but it's supposed to be a square, I assure you. So this is a square and the magnetic field is applied perpendicular. So perpendicular goes this way, it should be 90 degrees to the plane. So here, I believe there will be some confusion with the term A vector that we talked about yesterday. So the A vector is always perpendicular to the plane. Another name, always perpendicular to the plane. I'm recording, right? Yes. It's always perpendicular to the plane. Another name for a vector that is always perpendicular to the plane is, you can call it normal of the plane. Normal, you know normal is 90 degrees, right? So normal is 90 degrees, a vector is always 90 degrees, always perpendicular. So another term for a vector is the normal of the plane. If you are given a plane if the sentence says the plane without the normal of the plane, you need to assume that we're just talking about this guy, not the vector. Okay, so when it says magnetic field B is applied perpendicular, so this guy is perpendicular to the plane, not the normal of the plane. Okay, so I can reword this in another way. Magnetic field B is applied perpendicular to the plane of the coil. I can say this differently. The magnetic field B is applied parallel. Alamak, banyaknya nak tulis. It's a parallel to the normal of the plane. It means the same thing. Okay, so that's my best handwriting. So magnetic field B is applied parallel to the normal of the plane. It means the same thing as what we have drawn here. So magnetic field B is parallel to the normal of the plane. What is the normal of the plane? It is the A vector. Your A vector is also 90 degrees. So these two guys are parallel. So it means exactly the same thing. So I hope that clears any confusion if you have any with regards to this. Okay, so again, A vector is always perpendicular to the plane. It can also be said as the normal of the plane. If you have a magnetic field that is parallel to A vector or to the normal of the plane, it simply means that the B is perpendicular to the plane, which is this guy, okay? All right, so now let's try to solve this. So it changes uniformly from 0.5 to 0 Tesla in 0.8 seconds. So you have dB dt, dB over dt, dB dt. So that is B final minus B initial. It doesn't say what is the final time, final and the initial time. So I'm just going to write delta T over here, which is 0.8. And your Tesla, the final B is 0. And the initial one is 0.5. This is over 0.8. So now you get a negative B. Is it negative here? Or dia buat macam ni. Okay, that's fine too. So here I'm saying delta B over delta T is equal to minus 0.5 over 0.8. Okay, so it's 0.625. So minus 0.625. The unit is Tesla over time, seconds. So that is your first clue. Sorry, it's not your first clue. You have N, you have area already. You have your delta B over delta T. Okay, so now let's go to our equation that we learned yesterday, which is this guy over here. So I'm going to expand this equation. Sekejap, dia nak cari magnitude kan? So magnitude sahaja. So we are going to ignore this negative sign. Okay, we are going to ignore the negative sign. So N is, our N is constant. Sorry, I need to expand the magnetic flux first, right? So that was what we did yesterday. So N, expanding magnetic flux, delta, I don't know what is changing yet here. I'm just expanding the equation. So magnetic flux equation is BA cosine theta, and I have delta T over here. Okay, so EMF, nak cari magnitude, you just modulus the whole thing lah. You just want the value. Okay, so N over here is not changing. B is changing. A is not changing. The area stays the same. Cosine does not change. Your angle of B with A remains the same, which is a cosine 0. So we can just ignore it. Cosine 0 is just 1. So here everything is constant except the B. So if I want to rewrite this, I can write it like this. So NA delta B over delta T. If I want to include the cosine 0, I can. So cosine 0, but I'm just going to ignore it. Delta T, okay, so let's see if we get the same answer as the schema jawapan ni. So N is 200. Our A is apa? 0.18 times 0.18. Oops, silap kira. Square. 0.0324. 0.0324. This is a meter squared. Our dB dt is 0.625. This guy is modulus. Kita nak moduluskan the whole thing. So I'm just going to ignore that negative sign. 0.625 Tesla over second. Tesla over second. This is meters cube. Meter squared. Okay. Did I miss anything? N 200 BA cosine theta. Cosine is 0. B with A is parallel. B over T is 0.625. A is 0.0324. Okay, so now I can start calculating. Times 0.625. So I got 4.05, which is the same, folks. Okay, so my answer is, the working steps to my answer is slightly different than skema jawapan. You can do it like this guy over here or the way that I did it. The way that we did it was we constant it, and then we just say, okay, dBdt is the one changing. So I'm just gonna focus on that guy. Whereas for this one, for this working step, so A is constant, we got that the same. Dia kira the magnetic flux initial and the magnetic flux for the final state. So BI A cosine theta, B final A cosine theta. So A does not change, so you're just going to use the same A, the cosine does not change. So you're just basically changing the B to get the different magnetic flux, and then you find the change in magnetic flux, which is always final minus initial. So 0 minus 1.62 blah blah blah. You get this in Weber. And then your EMF equation is N change in magnetic flux over the change in time. Since we know the change in time is 0.8, you just plug in the values. You can do this way if you find it easier, or you can do it my way if you like it that way. Okay, so dua-dua boleh. Dua-dua akan dapat full marks. Okay, next one. So a rectangular loop. So now we have a rectangle with sides 0.2 and 0.3. So our area is 0.2 times 0.3 is 0.06. 0.006. So my brain is not working. 0.06 meters squared. Okay. Lies in a plane which is perpendicular to the uniform magnetic field of magnitude 0.64. So it's saying that we have a uniform magnetic field. Tak kisahlah rupa dia macam mana, but it's uniform. So this is the B, and it's saying that the rectangular loop of wire lies in a plane which is perpendicular. So always with the struggle. Okay. Oh my God, what is this? What am I trying to draw? How should I draw this? Jadi takut. I don't know. Okay, this is supposed to be perpendicular. Sekejap, saya tak nak fikir. How do I draw this? Why is it difficult? Oh, okay, ingat dah. Macam ni. No, it's not working. Tapi korang tahu lah tu perpendicular. Oh my God, so bad. Okay, this guy is perpendicular. So we have a rectangular coil that is perpendicular to the B. So we know that our cosine theta is cosine 0 or equals to 1 lah. Okay, so it's at the maximum value. And we have our B is 0.64 Tesla, directed parallel to the normal of the loop's surface. Directed parallel to the normal of the loop's surface. So this guy, the normal is this way. The B is also parallel to the normal. This is the normal of the plane of the loop. This is your B. They are parallel. So this is what it means. So B and A have an angle of 0 degrees, which is what we just said. Okay, it's the same thing. Okay, in a time of 0.18, so we know that our delta T is 0.18. Yes, 0.18 seconds. The loop is then flipped such that its plane parallel with the field. Okay, previously the plane was perpendicular. So this was situation initial, situation I. And then situation final, let's draw it down here. I doubt that I can draw it, but I will try. So this is the same B, the B does not change, but our loop kita flip dia. So it will be looking like this. So macam ni, macam tu. Okay, so now where is my normal of the plane? My normal of the plane is this way. This is my A vector, and the A vector with the B vector has an angle. The angle between them is 90 degrees. Again, the A vector and the B vector has an angle of 90 degrees. Ayat dia cakap the plane is parallel with the field. This guy, yes, it's parallel to B, but the A vector is 90 degrees to B. So our angle should be cosine 90 degrees. Okay, so our theta is 90 lah. So here we can say that we can continue with the same A, but we can say that our cosine changes. Okay, so here our cosine changes because that's the most easiest change that I can see over here. So let's try to expand that in the equation. So A is that cosine changes from cosine 90 minus cosine 0 is your change in cosine theta. Our A is the same. We are using the same loop. Our the cosine changes. What else? our B does not change. What is B? B is 0.64. Already wrote it there. And delta T is that. Okay, so now I'm going to try to expand the equation and put in the values. Oops. Okay. Is everyone okay? Is everyone following me? Senyap je korang hari ni.
Yes, Doctor.
Okay. Belum tengah hari lagi ni, jangan melepek lagi. Okay, so our equation for magnitude of EMF, right? EMF induced. EMF is equal to modulus it because we just want to find the magnitude. What do you call this? Magnetic flux over dt. So expanding this will give me N delta BA cosine theta over delta T. Okay, so now we know that our A is the same, our B is the same. The change is given by our cosine. So I'm just gonna make the change on the cosine and continue making everything else a constant. So EMF is equal to, our loop is 1. Oh yes, we have only one loop. 1 times A is 0.06, and then our B is 0.64, and then our cosine final minus initial 0. Lemak dia overlap. And then over time, which is 0.18. Okay, so let's see if we get the same answer as our schema 12. So cosine 90 is a 0, cosine 0 is a 1, 0.64 times 0.06. So the answer is, oh sorry, divided by 0.18. So I get 0.21 volts. Okay, which is the same. Here I only focus the change on the cosine. The skema jawapan ni dia suka buat macam ni, magnetic flux initial apa, magnetic flux final apa, baru dia cari jawapan dia lah. Okay, sama je. You can do it either way. Okay, so it both works as long as you understand. Okay, moving on. The magnetic flux that pass through 12 turns of coil. So N equals to 12 changes to 4 Weber from 10. From 10, so this is your initial, this is your final. From 10 to 4. From 10 to 4. Walaupun dia word macam to 4 from 10, don't get confused. It simply means from 10 to 4, which is this guy is the initial, this guy is the final. Okay, so what is that? Magnetic flux. Change in magnetic flux is magnetic flux final minus magnetic flux initial. Okay, so final is 4 minus 10 Weber. So that is a minus 6. The average induced current in the coil is I equals to 20A. What is the resistance of the wire? So it's asking you, what is the resistance? It gives you I, it gives you these bunch of values. For the delta T, I missed delta T. Delta T is 0.05. So with these values, we can find the induced EMF. Induced EMF is simply voltage. Okay, it's simply voltage. So if you can find the voltage and you know what the I is using V equals to IR, this is your Ohm's law, the famous Ohm's law, you can find out what is R. Okay, so let's do that. So here the change is in the magnetic flux, so that makes our life easier. So let's just start with EMF is equal to N. And okay, untuk jawab soalan V equals to IR, you need a positive EMF juga. So you need to use the magnitude only, okay? So in V equals to IR, please use magnitude only. Okay, so we will be modulusing this guy. D magnetic flux over dt, modulus this guy. So our N is 12. Our change in our magnetic flux is 6. I'm just going to make it positive. And then our change in time is 0.05. Okay, so that will give me 12 times 6 divided by 0.05. I will get 1,440 volts. And then V equals to IR. Dah senang dah lah. 1440 equals to 20 R. So divide by 20, you will get the R, which is 72. Okay. So soalan ni legit Dia bukan saja-saja nak buat soalan macam ni. Memang boleh tanya. They give you the current, they give you a bunch of parameters, find the EMF, find the resistance. Boleh, soalan ni boleh keluar. Okay. It's kind of famous too. This is 72 ohms. Okay, forgot the units. Nanti tak dapat markah full. Okay, so now, habis dah exercise untuk the first subtopic, which is induced EMF and induced current. We talked about, what did we talk about? We talked about the coil always does not like any changes. So if I have a magnet that is increasing the magnetic flux in the coil hates that, say I don't want you to increase, please go away. So it will try to repel. So dia akan, if this guy is a north, the induced guy will form a north to repel. So go away, right? So if my magnet is flipped, this is the north. Wait. Can you guys see? If you guys, what is this? Okay, this is north, this is south, this is north, this is my coil. So I am moving a magnet punya south, the butt, right? The butt of the south, moving towards the coil. So I am increasing the magnetic flux, but it's a south. So the coil hates this, blah, blah, blah. I don't like you, blah, 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 go away, right? So I want to make this guy go away, but now this guy is a south. So what do I have to do to make it go away? I have to form a north. I have to form a south so that it repels. So south with south repels. So when you know the polarity of your induced, if you know your induced polarity, you will know the direction of your induced current and also your induced EMF. And then what happens if I have a magnet that is north, this is south, this is the coil. I'm over here, but I move it away from the coil. So now the magnetic flux is decreasing. So obviously the coil does not like it. Dia memang takkan puas hati sampai bila-bila. So what happens? Dia cakap, okay, come back please. I want you to increase. So what should the coil do to attract this guy to come back, right? So it needs to form a south. So because this guy is a north, so if I form a south over here in the coil, the magnet will come, right? It will be attracted. So south with north will be attracted. So the induced polarity will give you the direction of your current. Okay, what happens if your magnet is south? The magnet is south over here, and this is your coil. It moves away from the coil. So now, obviously, the coil hates this, says come back, right? Says come back. So what should I do to make you come back? This guy needs to form north, right? So forming a north will attract the south. So this gives you the direction of your current. So that's one way of finding the induced EMF, the induced current punya polarity. And from that, you can find out what is the induced EMF juga. Because remember, EMF flows from the current flows from positive EMF to the negative. You know the direction of your current, you will know what is your positive and negative. Okay, so that's my best way of finding the direction. If you find other ways more comfortable, I mean like it's more easier for you, so use that. Doesn't matter as long as you understand and everything makes sense. Okay, there's no perfect way of doing it, whatever works. Okay, so now we are going into motional EMF. Right, I'm going to prepare myself to explain this. It's kind of hard for me at least. Okay, so motional EMF. What is motional EMF? So first, let's talk about the word here. So we know that EMF can be induced when we have changing magnetic flux, right? Changing magnetic flux. Changing gives us induced stuff. Induced magnetic, induced magnet, induced what do you call it? EMF, induced current. Gives us a bunch of induced stuff. So gives us induced EMF lah. Kita cakap kat sini. So you know that you always have to have a changing magnetic flux. When your magnet is constant, it will not generate any induced EMF. So that was the basis for all the stuff that we learned earlier. So now we are going into another topic, which is called motional EMF, whereby we produced induced EMF by moving a conductor. Previously, we moved a magnet, right? We moved a magnet, we moved the coil. There was some motion between a magnet and some motion between a conductor, a coil. Magnet and coil, that was what we talked about. Here, we are moving a conductor in a constant magnetic field. So this is the difference between what we learned previously, magnet and coil, moving. We have the magnetic flux. This guy is moving a conductor with velocity v in constant b. So this is the situation here. Okay, so as a result, okay, benda ni terus masuk pula. Kenapa saya pergi slide ni terus? This is the one. Okay, so the situation is we are moving a conductor. This is our conductor. Okay, moves at velocity v in a uniform magnetic field. So the dots over here or the bullets over here tells you that the magnetic field is uniform and it is out of the page. It's towards me, right? Towards me or towards you. So out of the page, towards me or towards you. So we have that B going on here. We have a conductor that we are pushing to the right. So that's the situation over here. Okay, so when I move this conductor, right? When I move this conductor, I am moving it with velocity V and I am also applying F applied. Okay, so ada dua benda kat sini. Kita ada velocity of the conductor and of course if I want to move it, I will apply some force, right? So that is my F applied. Okay. So a straight conductor of length L moves perpendicularly. So this conductor is perpendicular to the magnetic field. Why is that? Because this is our B and this is our conductor. Conductor kita macam ni. Okay, so the angle between them is 90 degrees. So it moves perpendicularly, walaupun ke kanan, tapi dia tetap perpendicular. Walaupun dia move ke sini, dia akan tetap macam ni. Dia tetap 90 degrees lah, all the time 90 degrees. So with a constant velocity through a uniform magnetic field B, the electrons in the conductor experience a magnetic force. Okay, so now let's go back to our chapter 19. This is why. Yes, okay. So chapter 19, we talked about FB magnetic field for a charge which is QVB. Chapter 19 and then there was another equation for FB which is BIL, if I'm not mistaken. So this is if you have a conductor, this is for a charge. But untuk situasi ni, for this situation, we are using the equation for a charge because we are talking about the charges inside the conductor first. Mula-mula lah, mula-mula. So we are talking about the charges in the conductor first. So again, from our right hand rule, um, what was it? From our right hand rule, we know that we have FIB, and then I will respond to I is current, right? So I is current, V will always be the current punya direction because we are talking about the charge direction. Okay, so this is our charge. Let's say I have a single charge over here. This is my V, right? This is my V. So that is the direction of my charge. Okay, walaupun conductor dia straight, tapi saya tengah tolak ke kanan. So direction of the charge is to the right, walaupun macam pelik sikit. But the direction of the charge is to the right because I am pushing the charge. Okay, so charge is moving to the right. So this is my V. Okay, so I have my V over there and I have my B, right? So this is my B. Okay, FIB, this is B, V or I. So B is towards me. V is that way. So my force, wait. So my force is V is this way. Susah lah. Okay, so F is down. F is downward. Korang try. F is downwards. So here F is downward. Okay, F is downward, but this FIB is for a positive charge. It's for a positive charge. When we talk about the charge and we want to know what is direction of the force acting on the charge, the FIB right hand rule gives us the direction for a positive charge. So if I wanted to know what is the direction for an electron or a negatively charged or a negative charge, if I get a force that is going down, I just say, okay, if this guy is negative charge, so the force is going up. So it's just the opposite case. Or I can use my my left hand and use FIB juga and find out that, how does it work? I is to here. This is my B, so my force goes up. Okay, so this is the direction of what my negative charge should go, force. This is the force. This is the direction of the negative charge punya movement, okay? So F goes up for a negative charge. If I use my right hand rule, V is like this, and then it's like that. So my F is down here, but this is for a positive charge. So if I wanted to know what is a negative charge, I just say, okay, F is going to be upwards because it's the opposite for a right hand rule. Okay, so I hope that clears things. So here, using my right hand rule, I find out that the movement of electrons should be going up. The movement of electrons should be going up. Oh my God, what happened? Oh no, it happened again. Oh man, I always forget how to figure out this stuff. Setiap kali lepas kelas, lupa diri. Okay, jap. Let me try. Bencinya. Sekejap korang. Kelas tengah cerita benda susah. Keramnya. Okay, let's try. Okay, tak boleh. Sekejap So I need to shut this down first. So I'm going to save it. Okay, sekejap tutup sekejap. Tutup all PowerPoint presentations. Buka balik. Okay. Now I'm going to try. Sebenarnya every time it happens that way, sebenarnya salah saya sebab saya tertekan something, but I don't know what it is. Gampang betul. Okay, jap. Oh, it doesn't work. Yeah, it works. Okay. So it's not my tablet's fault. It's me. I'm just postponing on figuring out. Malas nak fikir. So hopefully saya akan belajar dari kesilapan and figure it out. Okay. Okay, where were we? We were talking about motional EMF, and I told you that our force of the negative charge should be moving upwards from our right hand rule. Right hand rule terbalik ataupun left hand. Pakai left hand tapi sama right hand rule punya FIB. Okay, so let me padam dulu benda lah ni. Let's talk about the charge first. So I want to know what is the direction of electrons or negative charge, because in a conductor only electrons can move sebenarnya lah. But you don't have to know that much lah sebenarnya. Okay, so basically I just want to know what is the direction of electrons. So if my electrons semua nak ke atas, hello, kenapa tak jadi balik ni? Okay, semua nak ke atas, which means that I will have a net positive. Kenapa gendut ni ah? Tadi dah elok lah. Oh, it's not working again. Okay, I got it. Yes. Yes, okay. Okay, so everyone wants to go up. I mean, all the negative charges wants to go up. So it leaves me with positive down here. Remember, if we have a conductor that is neutral, we have same amount of positive and negative. So if everyone wants to go up, if all the negative charge wants to go up, all the positive will be abandoned, and contohnya kita ada 100 lah. Kita ada 100 charges, 50 positive, 50 negative, 30 nak naik atas, 30 negatif nak naik atas. So that leaves me with 30 positif kat bawah. So let's say this is like this. Positif, negatif, positif, negatif. Kita buat 8 lah. Negatif, positif. Okay. So 2 orang ni diperpakat. No, 3 orang ni diperpakat. Okay, let's go up. Let's go up and move by the force of B. So that leaves me with positif yang tertinggal kat belakang ni. Sebab sekarang ni semua negatif, semua nak duduk atas. Negatif macam ni. So yang positif ni dia macam terabai. Terabai sangat. Tapi dia tak bergerak lah basically. So dia akan tinggal kat bawah. So when this happens, you are actually creating a potential difference. So now this conductor, dia ada polarity. This is a negative, this is a positive. Okay, it is a negative up there, positive down there. How did I know why it's negative up there? Because from our right hand rule, we found out that the force is downward, but since this one shows us a positive charge in direction, whatever that we get from the right hand rule should be the opposite, so the force goes up. So the electrons goes up, which means that the downward part of the conductor becomes positive. So now we know that we have a positive polarity over here, negative polarity over here. Okay, so that is one part. So now when we have this positive and negative, as the negative charges accumulate at the upper end, a net positive charge exists at the lower end. Okay, we talked about this. And then ada lagi cerita dia. Okay. As a result of this charge separation, an electric field is produced in the conductor. We know that electric field force is F equals to QE, or E equals to F over Q. So mana-mana lah, F equals to QE lah. Kita nak tahu pasal force kan. So here kita akan equate FE with FB. Sama macam mass spectrometer that we learned in chapter 19. We equated force of electric field and the force from magnetic field. So this is QE equals to QVB. Okay, so now the Q cancels out, so I can say E equals to VB or V equals to E over B. Mana-mana lah, asalkan you know this equation. This one, this is the main one. So FE equals to FB for the motional EMF. So you end up with E equals to VB or whatever that you want to arrange it. And your delta V You know that delta V potential difference is E times D. We talked about this in chapter 16. Potential difference is E over D. Sorry, potential difference is ED, or equation yang kita belajar is E delta V over D. Mana-mana sama je lah kan. So here, using this equation, I want to know what is the potential difference in this conductor. So I substitute VB into here, okay, because I know what is the velocity, I know what is the magnetic field. So, but I don't know what is the E. So I substitute this guy into this equation. So I will get delta V equals to BLV. So is it important to derive? No, not really. You can just memorize. But I think it is important to know how the conductor forms a potential difference. Penting. Knowing how the conductor, this conductor, forms the potential difference is important. So what you need to know is, what is the direction of electrons? That's your first step. Okay, the first one is knowing direction of negative charge. I keep calling it electrons. Negative charge. Number two, after that we said there will be Fe will be equal to Fb. Because of the potential difference, we will have electric field. Tapi kita tahu force magnetic field pun ada. So Fe equals to Fb, which is QE equals to QVB. And then from here, we can know what is delta V, which is BLV. Okay? So these are the 3 steps in knowing the motional EMF punya potential difference. Okay. So that is, I want to make this together lah. Kenapa di separate? Kejap. Tak boleh pula. Sekejap. Copy. Let me write it here. Okay, so BLV, let's talk about BLV a little bit. So BLV, delta V equals to BLV or EL. B is your magnetic field that is constant. Here we have a constant magnetic field. What is L? L is the length of the conductor and V is the velocity of the conductor that you're pushing, right? So the lower end is at a higher potential. Remember, higher potential means positive than the upper end. So the upper end is negative. This guy is positive. So this guy has high potential, high V. This is low V. Okay. So this is like recap sikit lah chapter 16 and a little bit of chapter 19. Okay, so another way to, how do I see this? Okay, I wrote it here. As the bar moves to the right, the area of the loop increases by L delta X. So, okay, so the area of the loop, remember when we talk about area or the plane of the loop, we are talking about the coil. So this looks like a coil, right? So when I move the conductor, this looks like a coil. So when I move the conductor, I am actually increasing the area of the coil. So I increase it by V times delta T. V is meter over time. When you times it with the time, meter over second, times with second, it cancels out. So you are expanding by some meter over here. So this is distance meter. So it increases by L times delta X. So this meter is delta X. We call it delta X. Okay, so V, velocity, times with time, times with the change in time, gives you delta X. So V is distance over time, times with time, you get the distance. So distance is delta X lah. And the magnetic flux increases by BL delta X. So remember, magnetic flux is BA cosine theta. Here, everything is perpendicular, so let's just ignore this. B is constant, your A changes. So your A changes by delta X. So your magnetic flux is this way. So delta magnetic flux is B delta A, where delta A is given by B L delta X. Sorry, tak nampak sangat. B L delta X is delta I magnetic flux. Okay, do you have to know this? Tak payah, tapi I think it's important for you to understand so that bila korang dapat soalan pelik-pelik, korang boleh jawab. So that's the main reason why I'm explaining this thoroughly. Okay, so again, the delta V is BLV. If I substitute this into magnetic flux, this becomes B delta A. Remember, the length of the conductor does not change, so only the width changes, right? So the width changes by delta X. So your area is L dx or delta X over time. So you get BLV juga sama. L times dx is BLV. Velocity, not voltage. Okay. So, okay, let's do a mental recap of what we have learned so far. It's a little bit much, I think. Okay, so we talked about this guy. First of all, we need to know the direction. I need the figure. Okay, you can go away first because you are easy. Okay, so first we talked about this is the situation. We have a conductor. This conductor forms a coil, right? This coil or this conductor with a wire extending here is in a constant magnetic field B. Okay, so when we have B and when I move a charge, I am actually producing something like a current. I am moving the charge to the right. So using my FIB right hand rule, my V is to the right, my B is towards me and my force is downwards. This gives me the direction of a positive charge. But here, we can only move a negative charge in a conductor. So I am talking about negative charge. So that means the force should be going up. So negative goes here, positive goes here. So it creates a potential difference. So potential difference is delta V. It's not velocity, it's potential difference, delta V, right? Forms a delta V. And then because there is a potential difference, I know that there will be electric field. The electric field, I want to equate it to FB and I will get this equation. Okay, so from this equation, I can cancel out the Q. I will get E equals to VB. V as in the velocity. V as in the velocity. So delta V is equal to ED. So just substitute that, which is V velocity, B and D. D is just delta X. Right? Betul. What am I doing here? So E is VB, D is L. D is L? Kenapa je lain ni? Sekejap EL, ED. Oh, D is the conductor, betul. D is the conductor. So this is confusing. Saya tak patut cakap D lah. D is what we talked about for delta X. This is EL. Okay. So E is VBL. Kita nak hilangkan B. Okay. So, or BVL, velocity. Okay, so you don't have to derive, you can just memorize, but I feel like it's important to distinguish between potential difference and velocity. So you need to know this equation by heart. So this is potential difference in voltage. This is velocity. This is length of conductor, magnetic field. Okay, so that is for finding the potential difference and finding the potential difference of the conductor. And then we talked about EMF induced is N delta magnetic flux over time. And here, when we expand this guy, it's BA cosine theta. Here, the only thing that is changing is the area of the loop. And I know that my area, change in area is L delta X. So I just substitute that into my equation. So I will be getting something like this. BLX over dt, which is also BLV. Sama. Okay. So this guy and this guy is the same. If you're not connecting the dots yet, it is the same. So kalau rasa benda ni macam not intuitive and you like this equation better, you can memorize this. But you have to know that this means delta V juga. Okay, so EMF also means potential difference. And it can be used with this equation as well. You still get BLV, okay? So that is the two things that I want you guys to connect. Okay, so that is done for motional EMF. So now when we have motional EMF, the conductor behaves like a battery. So this is our conductor sebenarnya. Positive, negative. It behaves like a battery. So you know that when we have a battery, we will have flow of current. So the current flows from the positive to the negative. If the wire has some resistance, and we have learned this, we know that if a conductor has some resistivity to it, so usually they will give you what is the R, or they will give you the I and you will find out what is the R. So I equals to EMF over R. You know that the EMF is BLV or EL or ND or DT. So over R. Okay, so you get the current. I know it's a lot of equations and it's a lot of understanding new stuff. But yes, but memang kena. Sorry. Okay. So any questions about motional EMF before we move on to knowing the direction? Ada tak? Ada?
InsyaAllah tak ada, Doktor.
Everyone is like dying. Okay, let's take a 7-minute break and come back to motional EMF lenses law. Okay, 7 minutes, 12:07, please come back. I know you guys can't drink or whatever, but I know you need time to break. Sekarang dia untuk Prof of a post-op position and dia cakap akan bagi tahu dulu. Excuse me. Equals is this. Hmm. Increases. Okay. Okay. Equals so L delta X. So A is L delta X. Delta X over dt is velocity. Mm, okay. Mm, oh, it's already 12:09. Okay, I hope everyone is back. Resembler. Okay, so to summarize, motional EMF in magnitude sahaja, we have not talked about the direction yet. So the summary is, first we need to find out what is the negative charge for the direction. to know the potential difference, whether the top part of the conductor is positive or negative, and whether the bottom part of the conductor is positive or negative. From there, we will get a potential difference. When we have a potential difference, we will have electric field, and the electric field will be equated to the the force of electric field will be equated to the force of magnetic field. And from here, we will get the potential difference is actually induced EMF, and induced EMF is BLV. B is magnetic field, L is the length of the conductor, V is velocity. This is your L, right? Or you can use this equation and D change in flux over the change in time. Here, our flux changes because the area changes by length times delta X. So this is your delta A. Okay, so that is your change, and this equation is equal because velocity is delta x over dt, and we have a delta x over dt over here as well. So they are the same thing, but different forms sahaja. And BLV can only be used for motional EMF because we have the velocity, whereas the equation over here, you can use it for the examples that we have learned earlier, which is the magnetic field with a coil and so on. But BLV is exclusive for motional EMF, but they mean the same thing. Both are induced EMF. Okay, so when you have induced EMF, you will also get a battery because EMF is simply a battery. So if you have a positive over here and a negative over here, you know that your induced current will flow from the positive to the negative because this is induced EMF. Therefore, this is induced current. Okay, it's not your regular current, it's your induced current from the induced EMF. And then from here, they will ask you to find what is the resistance of the coil, or what is the resistance of the wire connected to the conductor. So you can use this equation, I equals to V over R, or V equals to IR. And you know that the V for a motional EMF type of problem, the V is always BL velocity, BL velocity. So don't get that confused with voltage. All right, so that is the summary for that. Now we are moving on to finding the direction of motional EMF. Tadi punya example dots. So this one is a dot, this one is an X. Okay, so we have both. So let's start with dots first. So my conductor is moving. Now my conductor, tidak, kita cakap pasal the first one first. Okay, this one and this one. Okay, so this is the first example that we should go through to find the direction of the current. Assuming that you do not use the 3 steps that we discussed just now. So you don't use the 3 steps, you won't know what is the direction of current. However, from here, you can find out using Lenz's law. So tadi tu kita find out using a bunch of equations, right? And the knowledge that we had from previous chapters. So now we can use Lenz's law to determine the direction juga. So how you do it is, as the magnetic bar moves to the right, the magnetic flux through the circuit increases. So here, remember, when we have when we have a magnetic field, I start with a square coil. So this is my coil. So my coil ni, saya boleh expand coil ini special. So the first step is I have this coil and placed perpendicularly in a magnetic field. So the angle between B and A is 0, or the angle between B and the plane of the coil is 90 degrees. So they are perpendicular. So my coil can be expanded. So when I expand my coil, mula-mula saya hanya dapat 2 lines of B, or I only got 2 lines. When I expanded the coil, now I can get 4 field lines going into the plane of coil. Remember, magnetic flux is always BAN, B times A. So the bigger your A, the more magnetic flux that you have. or the bigger your B, the more magnetic flux that you have. So in this case, my A changed, my area increased. So my magnetic flux, the amount of field lines that can go through my coil is more. So that means my magnetic flux also increases. Okay, so this is the situation over here. Assume that we start with this size of coil. This is my initial size of the coil. Now I move it to the right, my area expands. My area now expands to this much. So it expands, so it can allow 1, 2, 3, 4, 5, 6, 7, 8, 8 field lines into the plane of coil. Previously, it was only 6. When I expand the area, it became 8. So now the magnetic flux increases. Okay, so when it increases, what happens to the coil? The coil is always a very negative person. It does not like changes. So the same thing happens. It does not like changes. So what happens here? It wants to oppose the change. So wants to, yeah, what am I trying to write here? The coil is unhappy. Okay, we start with that. Opposes, wants to oppose the change. Wants to oppose any changes. Wants to oppose any changes. Okay, so in this case, the changes is an increase in magnetic flux. So no, I don't like this. Go away, right? When we have, okay, now saya akan cuba imagine this from the side view. Wow, the side view is very bad. So this is my side view of the coil. Side view, side view, Okay, so if this is my side view, so this is my B. Okay, so B ni B yang datang daripada environment. I want to do this in a different color. So B is this way. Okay, so the coil does not like this. Of course, dia akan try to repel. So if B is this way, kita akan cakap, okay, this is the north way, this is the south way. Remember, if you have something increasing, the coil hates that, it wants to oppose, so it will try to repel. So if it wants to repel, it will have something, it will form a negative, sorry, it will form a north pole over here to repel. Repel, okay? So we'll try to form a north pole over here to repel the change. So this is N, and this is the N from induced. So when I have an induced N this way, I will know immediately what the direction of my current is in the coil. So induced magnetic field gives me induced EMF, gives me induced current. So I know that the current should flow clockwise in my coil. So now I flip it back. I know that my current flows clockwise in this coil. This is the induced current. So kena ada imagination sikit lah yang ni. Saya tak tahulah macam mana nak tolong part ni. So again, I'm going to repeat myself. Number one is we have an increasing magnetic flux, right? Number two, coil does not like this, wants to oppose any changes. So it wants to form, it wants to repel this change. So it wants to repel. It wants to decrease the magnetic flux by repelling. It wants to decrease by repelling. Okay, so it repels by forming north pole down here to repel the north pole from the magnetic field daripada environment lah. So when you have a north pole going down, your induced current will be flowing clockwise. Okay, so this is your induced magnetic field. So your induced current is clockwise. Okay. So induced current follows the right hand rule screw. Okay, so that is one way of doing it. Untuk yang ni saya tak tahu macam mana dia buat. Okay, let's move on. Move on terus kan. Okay, so another one. Now, this is the same situation, but now our velocity is to the left, which means that our area decreases. Okay, our area decreases now. What happens when our area decreases? Our magnetic flux decreases. Okay, so again, the coil is a very negative person, does not like any changes at all. Tak suka perubahan. Dia suka jadi old school. So coil is unhappy, wants to oppose the change. Again, walaupun change dia decrease pula. I don't care, I still don't like it. I want to say wants. Where is wants? Wants to oppose the change. Always. Always dia tak kira. Asalkan korang, kalau tak bergerak baru dia happy. So wants to oppose the change, always. So what happens? I want to increase the magnetic flux. Come here. So increasing, I want to attract. I want to attract. So when I want to attract, so let's imagine this sideways. So this is my coil, this is a side view. My induced, tadi kita punya color apa tadi? Color untuk environment is pink, induced is green. Okay. Oh, saya silap pakai warna. Okay, so environment is out of the page. So this is the environment punya B. So what is the induced B here? The induced B wants to attract, right? Sebab benda lah ni dia berkurangan, so it wants to naikkan balik. So what it does is it forms a B that is similar direction to the one that is berkurangan. So it wants to make it go back to normal again. So B normal is as in increasing. So this is B induced. So okay. So now when I have B induced this way, this is my B induced. It is out of the page juga. So I will have a current that flows anti-clockwise. So this is the direction of my induced current. Nampak macam senang kan? Senang kalau tahu macam mana how to use the right hand rule. And understand that the coil always opposes any changes, okay, or the conductor. Oh no. Okay, so decrease, it wants to increase, so it will attract. Here, yes. Now, can you go? Oh my God, what happened to your face? Okay, bye. Mommy teaching. And then, tadi the first example, we talked about magnetic flux increases, so does not like this. It wants to repel. It wants to make it go decrease, so it will repel. Okay, so that is when we have increasing area and also when we decrease the area. So what happens when our B is a different direction? Our B is a different direction now. Okay, so our B is a different direction. I want to use this slide without the notes. What time is it? Okay, we have time. Okay, self-inductance next class. Okay, I hope everyone is still with me. I know it's very heavy, but kalau tak nanti korang tak belajar, lagi susah kan? So please stay with me. Oh my God, why isn't it erasing? Okay. Okay, so now we have, tadi kita ada B that was into the page, sorry, out of the page. This one is into the page. So let's discuss this one so that we are clear on any directions. Okay. Okay. So now we have, okay, abaikan this polarity. So now we have a magnetic field that is into the page and a velocity that is going to the right, which means that our area is increasing, right? So area here, area is increasing. And this one, which means that our magnetic flux also increases. This one, area is decreasing because it's moving closer to the wire, so the coil becomes smaller. So area is decreasing. and your magnetic flux is decreasing. Okay, so what happens to the coil? How does the coil feel? The coil feels unhappy, it does not like this change, so it wants to oppose whatever change that is going on. So here we have increasing. So what does the coil want to do? It wants to oppose this, it wants to make it decrease. So it will try to, wants to decrease, therefore it will try to repel. Okay, coil is unhappy, wants to increase, therefore try to attract. Kacau betul lah gendut ni. Okay, so now I will try to draw it sideways. This is for the first example. So this guy area is increasing, but it is north. It's increasing, but it's north. Down, the north is down here. This is the south. This guy, this is the north, and this is the south. It's the same situation, except that one is increasing in flux, one is decreasing. So increasing flux, we know that we want to attract it. Sorry, increasing, we want to decrease it. So we will try to repel. I'm too distracted. Go, let's go out. Let's go out. Let's go, let's go. Before you, okay? Mommy's getting it. Okay, so I'm back. Okay, so this is our coil. This is the B from our environment. Kali lain pula. B from our environment. And this is the South Pole and this is the North Pole. This is the B from our environment. Oh, this color is not helping. Music. B. Okay, so now I want to know what is the induced magnetic field, right? So induced magnetic field always wants to oppose changes. So this one is increasing, so I want to decrease it. So I want to repel. I want to repel, so I should form, this is a south, so I will form a south down here as well. I want to repel because this guy is increasing. Walaupun dia terbalik, it's increasing. I don't like that. I want to repel, so I will be repelling a south. I am repelling a south. And then this guy, area is decreasing. I don't like that. I want you to increase. So dia cakap come back south, come back. So it will form a north to attract the south to come back so that it increases the flux. So this is the polarity that is formed. Okay, so now that we know what is induced, I will know that N going up gives me anti-clockwise direction. Anti-clockwise, so this is the direction of my current. And for north that is going down, I will form a clockwise direction of current. So this is a lemma. Oops. Okay. So this is the direction of my current induced. Induced I. Induced I. This is induced B. Induced B. Okay, was that okay? Is everyone clear on how to find the direction? Magnitude was a bunch of equations. Direction is using your right hand rule and knowing whether the flux is increasing or decreasing. Is everyone okay? Everyone still alive?
Doctor,
Yeah.
I don't understand.
Which one?
Uh, About the picture, what do you mean by the direction? The I direction or the V or the F? I don't quite get it.
Yang mana? Yang mana? Lagi sekali, Umar.
I don't understand which direction that is say we are using the hands rule to find it.
Betul. Oh, you tak faham from right hand rule tu macam mana boleh translate jadi current macam tu, is it?
Yes.
Okay. Kejap. Okay, remember that we learned, saya buka jap slide from chapter 19. Okay, so we learned about coil. Okay, we have like several structures. The first one is this guy where I is your thumb and B is given by your fingers, right? This is the one. Okay, and then there was a second setup, which is the coil. The coil, so saya ajar this way. So this is your thumb, and the direction of your fingers will give you, cakap, the thumb, and this will be your fingers. So the direction of your fingers will give you the direction of I, and the direction of your thumb is pointing towards the, this is your I, this is your north. Okay, so there are two versions of the right hand rule yang saya ajar. Or you could use this one if you understand this one lah. Kalau untuk yang ni, the fingers points towards the north, the thumb gives you the current. But I like to use this one. So boleh je mana-mana. But you need to know when you have a north, it will go, when you have a north, it will go, we had this formula as well, anti-clockwise. This N gives you north. We have clockwise. This S gives you south. Basically, anti-clockwise to NT gives you always a north pole, and a clockwise direction of south. Sorry, a clockwise direction of current gives you a south pole. So now, if we want to use this, boleh juga. Or you can use the right hand rule. The right hand rule is your thumb points towards the north. Right hand rule, thumb points towards the north, and your fingers will give you the direction of current. So this is the first one that I taught you. This is the second one. This is the third one that I did not teach you betul-betul. So this is another way. So I want to use number 1 and number 2 for this type. Okay, so let's go back to the problem. Faham tak yang ni? Cara nak tengok yang ni dulu. Is everyone
Faham?
okay with one? Okay, faham eh? So now we go back to our chapter 20. Right? So now I know that my induced B is south and north over here. So if my north is pointing upwards, right, my current will be flowing anti-clockwise. You can use number 1 method or number 2 method. Okay, number 2 method cakap anti-clockwise is north. Okay, and clockwise is south. Sorry, the south pole. Okay, so here we know that kita tengok pada atas lah. Saya lupa nak cakap. Kita tengok pada atas. So the north is going up. So my current will be anti-clockwise. So this is what I got. I got an anti-clockwise direction of current. Okay, I got an induced I. From my induced B, I saw that the N was going up. So when I know that my N is going up, I will get anti-clockwise from the top. I will see that the current is flowing anti-clockwise in the coil. This situation, I saw that my N was going down, and what I saw from the top is S. I saw from the top S, a south pole. So when I see a south pole, I know that the direction of current is clockwise in my coil. So this guy is clockwise this way, which is the same as this guy. Yang ni anti-clockwise. Okay, so this is the direction of I induced. And how did I determine that? I needed to know what is the pole of my induced B first. What am I seeing? Am I seeing the north on the top, or am I seeing the south on the top? Okay, so north kita tahu always anti-clockwise. When we see a south, we always know it's going to be a clockwise direction of current. So you can use this method or the right hand rule screw, whichever that is most comfortable. Okay, is that clear?
Yes, doctor.
Okay, so about the direction of current? I think okay sebab saya dah cerita balik pasal chapter 19. What about induced B? Was it clear? Are you guys okay with how to determine what your induced B is?
So far okay, Doktor.
Apa?
Okay saja.
Okay saja. Induced B okay saja. Okay. So again, if your area is increasing, you know that your magnetic flux is increasing. Coil does not like that. Dia nak decrease. Bila dia nak decrease, dia akan repel. And then bila area decrease, magnetic flux decrease. Coil tak suka, dia nak increase. So increase, dia akan try to attract. So depending on the pole of your magnetic field, if you are trying to repel, you need to form a south over here. So what you will see is a north up here. If you want to attract, you will form a north over here so that the north attracts the south, and you will form a south up there. So that is how you get the direction of current. Okay, so now let's do exercises. Before we end our class, we have 2 examples. Okay, that's great. So a square coil with side 5 centimeters. So this is 5 cm. This is 5 cm. Has n equals to 100 loops. Uniform field of B equals to 0.6 Tesla with its plane perpendicular to the field. So it doesn't say if it's going out of the page or into the page. I can just draw it like this. Tak kisah. Asalkan perpendicular. A total resistance on the coil is 100. So it's saying that the resistance of the entire coil is 100 ohms. The coil is then pulled at a constant speed to a field-free region in 0.1 second. So it is pulled, oh, the coil is pulled. So dia cakap the coil ni, dia mengembara selama 0.1 second. Tak tahulah kenapa. So dia kena pull lah. So this is the velocity of the coil. The coil moves as a whole. This is what I'm getting from the question. So constant speed to a field-free region in 0.1. Calculate the rate of change of magnetic flux through the coil. So rate is over time, change, so delta, this guy over delta t. So this is what you are trying to find. So we know that this guy is n delta BA cosine theta. We can just ignore that because it's perpendicular over time. We know that time is 0.1. We know what is B. Let me write that down first. Delta T, N is 100. The B is a constant, 0.6. The A is changing. No, it's not changing. Oh, here we have EMF. Oh, dia buat macam mana? Area dah ada. Okay, area is 5 times 5, 0.05 times 5. Sorry, 0.05 squared, which is 2.5 millimeter squared. Okay, BA cosine theta, 0.6, 2.5, cosine 0, 0.1. Okay, so we got that. The induced EMF in the coil. So it's asking what is EMF, which is N change in magnetic flux over dt. Oh, sorry. Magnetic flux tadi N. This is my bad. Magnetic flux tadi N. Yes, I forgot to highlight this. BA cosine theta. Okay, remember when we have the EMF equation, it was always this way. So N is not part of magnetic flux. Yeah, it's not. So this guy is this guy, BA cosine theta. So I hope that highlights, I want to highlight this to you, so don't get that confused like I did. Okay, so the induced EMF is N, change in the rate of magnetic flux. So we got this 1.5. The current induced is 1.5 over 100. Pretty easy, I think, because you just had to find out what is the change in magnetic flux over time, and then just use it with the N, and then V equals to IR. Kind of easy lah. Tak payah cari direction. Saya rasa bila dia start cakap pasal direction is when it becomes a little bit hard. Using the equation is okay. I think it's okay because it's just putting in the values. So here, remember you got a minus sign over here. So this should be a minus, but when you use it in the V equals to IR, your V is a positive. So selalunya I would say this equation should be find the magnitude of induced EMF. If we are going to moderate this question, I will highlight to them that they should include the word magnitude. Okay, sebab selalunya negative ni untuk direction. So just find the magnitude if there is no direction involved. Okay, magnitude. Okay, moving on. So this one ada direction tak? Yes, ada. Okay, so this is expected. A metal rod AB moved vertically at 2 meter. This is your V, meter per second, along 2 vertical rods. So this is your vertical rod over here. The rod is in brown color through a uniform magnetic field of 1.5 directed into the page. So I want to ask you guys to do this one before we end our class. We have time, 20 minutes. So I hope everyone is awake now. Okay, so let's say our B is this way and our B is 1.5. The length of the rod is 40 centimeter. I need to get rid of the solution before you guys see it. Okay, so the direction of B is that way. The length of the rod is 40 centimeter with a resistance of 1.5. So it's saying that the L is 40 centimeter and R is 1.5. Is the R in series or is the R in parallel? That's the question. Kenapa dia cakap macam ni? If the length of the rod is 40 centimeter with resistance, but the resistance over here. Kind of weird how they portray the question. Kejap If the length of the rod is 40 centimeter and is connected, let's just say like that, is connected to a resistance, to a resistor of, okay, calculate the induced EMF, induced current, and direction of the current. All right. So I'm going to assign this to people yang jarang kena panggil. Let's see. We only have 32. Where is everyone? Najwa. So Najwa lah ni.
Doktor,
Yep. Yes? Tadi ada orang panggil. Who was it? Hilang dah. Okay. So let's see. Nak Danish lah kat sini. Danish number 2, number B. And siapa yang jarang panggil? I think Shakira macam lama je tak buat lagi. Shakira. Ke Shakira baru je? Tak ingat. I think YNE baru, Fairuz baru juga. Nisha ada juga saya panggil. Hidayah macam jarang. Hikmah was last time Christina dengan this one tak ingat. Okay lah, Shakira lah. Shakira, is Najwa, Danish and Shakira here?
Yes, Doctor.
Tu siapa? Najwa
Yes, Najwa.
Shakira ada? Danish ada?
Ada, Doctor.
Okay, so dah bunyi dah, tak larat dah tu. Okay, sikit lagi. Lepas tu kita habis kelas. So Najwa buat induce EMF, Danish induce current, and Shakira cari direction of current. Okay, so using the lenses, yang approach tu lah, yang approach right hand rule tu. So I'm going to give everyone 10 minutes and then we will discuss. Boleh buat sama-sama ya. Jangan tidur-tidur. Okay, alamak tak cukup. 7 minutes. Sebab senang je. So 11:51. We will discuss this. 11:51. 12:51. Sedang sangat soalan first tu. Should be okay, 7 minutes. Two. Direction of current is ke bawah. Direction of current dah ada kat sini, tapi Syakira kena explain macam mana dapat. Downwards. It's increasing in flux. Okay. Okay, saya dah siap dah. Come back again. Okay, what time is it? Oh, 2 more minutes.
Doktor,
Yep.
macam mana nak tentukan yang A dengan B tu kan, yang mana charge dia positif atau negatif?
Yang mana charge dia positif atau negatif? You mean the potential difference ke?
Potential.
Ni siapa? Syakira ke Najwa? Saya tak nampak nama.
Syakira.
Oh, Syakira. Okay, Syakira. Okay, first. Tak apa, nanti kita bincang lah. Kita tunggu lagi seminit Seminit je kita bincang. So Syakira tak dapat lah macam nak kira direction dia. Ke dah dapat dah, tapi nak tahu lebih lanjut. Oh Syakira, dapat ke tak direction dia?
Tak, sebab tak tahu mana satu bahagian yang mana positif, mana negatif.
Okay,
Pening.
kalau tak pakai yang AB ni, pakai lens law, tengok direction of magnetic field sahaja. So saya kasihin So direction ni ada magnetic field. Is the magnetic field increasing or decreasing? Kemudian adakah coil, coil tak suka kan? So what will coil, apa yang coil akan buat? Kalau kita punya B is increasing, dia akan cuba decrease. Kalau our B is decreasing, dia akan cuba increase. So kat sini, is it increasing or is it decreasing? This is the V. Is it increasing or decreasing? Mana bentuk coil tu? So Syakira jawapan dia increasing ke decreasing?
Doktor, tadi saya punya ni tak dengar. Dia terpotong.
Okay. So sekarang ni saya cakap, saya kasih hint. Kita ada B kan? Kita ada B. Awak tak payah pakai yang potential difference tu pun tak apa. You just look at the magnetic field. Now you have a conductor yang moving downwards. So is your area increasing or decreasing? Is your area of the coil increasing or decreasing? Increasing ke decreasing Syakira?
Increasing.
Increasing. Okay. When your area increasing, your magnetic flux increases or decreases? Magnetic flux is BA cosine. If your area increases, does your magnetic flux increase or decrease?
Increase.
Increase juga kan? So magnetic flux increase, coil tak suka, coil akan cuba decrease. Macam mana cara dia nak decrease? Dia akan cuba repel. So kalau dia nak repel, apa yang dia perlu buat? Okay, tu hint dia. Apa yang coil cuba buat kalau dia nak kena repel something that is increasing? Tak tahulah Syakira dapat ke tak. Tak apa, nanti kita bincang. It's okay. Okay, Najwa dapat tak jawapan induced EMF?
Dapat.
Okay, so what is your equation?
Induced EMF sama dengan BLV.
Okay, which is 0.
Itu masukkan
uh,
nilai 1.5
1.5.
kali 0.4
Okay,
kali 2.
2. Okay, so your EMF dapat?
1.2 V.
Okay, 1.2 volt. Okay, thank you Najwa. Danish?
I equal to EMF over R.
Okay.
1.2 volt over 1.5 kilo ohm.
Kilo berapa?
1,500 ohm.
1 times 1000 lah. Okay. Jawapan I is?
8 times 10 power of negative 4. Minus 4.
Berapa tadi? Sorry tak dengar. 8 times?
8 times 10 power of minus 4.
Minus 4. Yeah, 1.2 divided by 0.5 times 10 to the 3. Oh, betul. Thank you, ampere. Alright. So dapat jawapan A dengan B, betul. Thank you. 1.2 divided by R. Okay. So now Syakira, the direction of current. Dapat tak from my hint tadi? Thank you Danish and Najwa. Dapat tak from my hint?
Doktor.
Tak dapat? Okay. Okay, so first of all, apa yang kita kena tengok kat sini is which one is our coil. A coil, dia kena bulatan lah ataupun square, dia kena bercantum. So kalau kat sini dia tak ada bercantum kan, so it's not a coil, so it is free end. So our coil is over here. Okay, so this is our coil. When we move our conductor, we are actually increasing the A. Okay, when we move conductor downwards, kan, this is our V, kita sebenarnya membesarkan the area. We increase the area. Okay, we increase A. And magnetic flux, kita kena tengok magnetic flux adakah dia berkurang ataupun meningkat. So magnetic flux punya equation is, warna ni tak nampak. Let's use black. So BA cosine theta. So this is magnetic flux. My B is constant, my A changes, which means that my magnetic flux will also change. So if my A increases, my magnetic flux also increase. If my B increases, my magnetic flux also increases. So kat sini, kita boleh view this in terms of area ataupun kita boleh view this in terms of magnetic field lines dalam coil. So kita nampak mula-mula kita ada 1, 2, 3, 4, 5, 6. Bila kita extend kita punya conductor, kita dapat 9B. Boleh view it like that, but yang paling senang nak tengok kat sini is the area. Area ni memang diberi length times area ni diberi ke? Oh, length ni diberi, yes, 0.4, sorry. So kita tahu our area is membesar. Okay, so daripada situ kita bukan nak kira dia punya value, kita just nak tahu adakah dia increase ataupun decrease. So now that I know that it increases, I don't care the value, I just know that it increases. So what is the feeling of the coil? It does not like something that is increasing, so it wants to decrease the magnetic flux. So this is what is going on. This is what we are aiming for. This is what the induced EMF or current will be. Okay, the induced EMF akan bergantung kepada pengurangan of magnetic flux. So macam mana kita nak kurangkan magnetic flux yang berlaku kat sini? So if I were to view this sideways, ni coil yang sama walaupun buruk. Alamak, sila kelok sikit lah. So because this is a square, right? Square, bukan square. So this is my coil. This is the direction of my B. My B is into the H. This is my B. The B is increasing because we know, our magnetic flux is increasing because our area membesar. So kita ada magnetic flux yang increasing. So what should we do? We want to decrease the magnetic flux. If we want to decrease something, we should repel. So first of all, I need to know what is the pole of my magnetic field. So this is south and north. North always at the tip of the arrow, south always at the butt of the arrow. And if I want to repel, okay, I want to reduce it, so I need to repel. So I need to form an induced magnetic field that is this way. Nak repel kan? Repel kena sama lah. So repel south with south. So what am I seeing from the top? My eyes is over here. I'm seeing a north. A north corresponds to an anti-clockwise. So I will get an anti-clockwise current direction in my loop. Okay, so is that okay for everyone? Syakira faham dah ke?
Faham doktor.
Okay.
Betul, tak faham.
Faham yang mana? Okay,
Yang soft. Yang soft.
Okay. Situasi kita kat sini, kita punya area increase. So kita tahu magnetic flux increase. Coil tak suka magnetic flux yang increase, dia nak cuba decrease. Kalau magnetic flux kita berkurang, coil tak suka, dia akan cuba increase. Tapi dalam situasi ni, dia nak cuba decrease. Kalau kita nak decrease something, kita nak tolak dia. When we want to decrease the magnetic flux, we want to push it away. Nak decrease magnetic flux kan? Nak push it away. So macam mana, how can I push away a magnet that has a south pole here? I can form a south pole sebab similar poles will repel, right? So dia akan berlaku penolakan. Dia nak tolak sebab dia tak suka magnetic flux to increase. So dia nak tolak lah magnetic field tu. Tolak. So as it will form a south sebab dia nak repel. South with south repel. So the top part is north. Top part is north. Kita always tengok daripada atas. Bila kita nak tengok direction of current Yang saya lukis dalam ni is from the environment. Ni V yang diberi. So the induced one, let's use a different color. So kita punya yang dalam environment is green. Kan? This is green. Yang di-induce adalah color purple. So what am I seeing? I'm not seeing the induce, I'm just going to see the current. Tapi kita nak bayangkan. So this is the induced magnetic field. Okay, so from this induced magnetic field, use my right hand rule. North towards me, current flows anti-clockwise. You can use your hand or you can use this method. So north towards me, use your right hand rule. Your finger points towards anti-clockwise. So this is the direction of your eye. Okay, so that's the second way you can do it. Okay, Umar, okay tak?
Kalau case dia area dia mengecil,
Kalau area dia mengecil, dia akan, okay, let's talk about that. Let's duplicate this. Oh, dah terlebih masa. Siapa yang kena go somewhere, you can leave. Kalau nak stay boleh. So kalau area dia mengecil, velocity dia kena ke atas, betul tak? Sebab kita nak mengurangkan area of the coil. So this is our new V, boleh abaikan V yang ni. So V is going up, area decrease. Area goes down, therefore magnetic flux also goes down. Okay, when we move the conductor up, we decrease the A. Therefore, we have magnetic flux yang berkurangan. Let me rewrite this. We move the conductor up, we increase A. And magnetic flux, area decrease. Magnetic flux decrease. Okay, sebab A decrease. Like I said, we don't really care about the value. We just want to know the direction. And if we want to know the direction, we need to know whether magnetic flux increase or decrease. Cara nak tentukan magnetic flux increase or decrease depend on BA cosine. B kat sini constant, A sahaja yang berubah. A berkurang, magnetic flux berkurang. Okay. So that is the first step. A decreases, magnetic flux decrease. So when we have something that is decreasing, the coil does not like this. Dia nak cuba naikkan magnetic flux. Macam mana kita nak naikkan magnetic flux ni? Kita kena tarik dia masuk dalam coil. Kita nak tarik magnetic field tu masuk balik dalam coil. Jangan pergi jauh-jauh because we want you to increase. So now instead of repelling, I want to attract. So this is what the coil wants to do. So if I want to attract this guy that is decreasing, I want to attract the south, I need to form a north down here because I want to attract. So I need to form, I need to form a north like this. So north with south berlaku attraction. Viewing from the top, if it is a north, I should be, viewing from the top, I should see a south, right? South dekat hujung ni. So I see a south, it should be a clockwise direction of current. Clockwise I. If you don't want to use this way, you can look at this part over here. We know that the current the magnetic field from the environment is X, and the induced one that we figured out is also X because we are seeing the south. is going into the page. It's also an X. So using my right hand rule that goes into the page, my I will flow clockwise. This is the direction. Dia jadi terbalik daripada yang tadi. Okay, so this is when the area decreases. Was that okay? We only
Okay.
depend on the induced magnetic field untuk direction of induced current. Induced magnetic field, induced current, induced EMF. Okay, so lagi satu soalan yang diorang boleh tanya. If my I is clockwise, what is the polarity of this conductor? Again, I should always flow from positive to negative. So it flows from here to here. So this will be my positive. This will be my negative if they ask you to find out the polarity of the conductor. Okay, that's it for class for today. Thank you for the questions and thank you for staying alive with me through this subtopic. Take care, selamat berbuka kepada yang berpuasa dan selamat lunch kepada yang tak. Okay, take care, bye. Bye everyone. Lambat sangat tu.
Thank you.
Thank you,
Bye.
Doctor.
Thank you, Doktor.
Doktor.
Thank you,
Thank you, Doktor.
You're welcome.
Thank you, Doktor.
Thank you, Doktor.
Welcome. Bye.
Thank you, Doctor.
Bye. Welcome.